So we're going to start the second half of our course, which is on trigonometry. And trigonometry is one of my favorite topics. It can be a little challenging the first time you learn it. It's kind of like learning a new language. And so this first section, we're really getting our feet wet with several different definitions. Trigonometry literally means triangle measurement, and it's sort of at its heart based on using triangles to make different measurements. But it's all about angles, and we're looking at measuring different angles and different types of angles. So in this section, I want to start with some of these definitions that are going to help us kind of understand what we're talking about. You've probably heard a lot of these terms before. I'm thinking probably back to high school geometry. A ray, I'll just draw a quick picture. So if you have a line that starts at one point and just goes on forever, that's what we mean when we talk about a ray. I won't give you a formal definition, but this is what we're talking about. If you put two of those rays together, that's when you get, of course, that's when you get an angle. So an angle is where those two rays come from one point and then emanate in different directions. The initial side is where we start drawing that angle. So let's see, I don't know if I have a formal definition, but we can say where we, or the side, I should say, let's do it that way. The side, we start drawing the angle. And this will make more sense as we go. We'll have some images and some examples. The terminal side would be the side or the ray we end drawing the angle. All right, and then of course the vertex is just like we would think of if we were using it to draw a picture in algebra. Vertex would just be the point, the common point where the two rays meet, and that's what forms your angle, right? So like in this little image right here, your vertex would just be this point right there. Okay, so an angle is in standard position if two things occur. So when we're drawing an angle, we're looking at it from a perspective using trigonometry, we usually work with angles that are in standard position. And so the first requirement to be in standard position is that the initial side must be drawn on the positive x-axis. And that's actually really important. And then the other condition to be in standard position is that the angle is drawn counterclockwise. Although we sometimes could draw an angle clockwise, and we'll talk about that in a few minutes. But the most important thing is that the initial side must be on the positive x-axis. I guess maybe there's one more requirement here, that the vertex must be at the origin. Maybe that's the other condition they were looking for here. The vertex must be at the origin. So let me take out this counterclockwise thing because I actually think that's not necessarily going to be part of it. The vertex has to be at the origin. Those are really the two pieces that you have to be in standard position. Every time we work with these, they're going to be in standard position. So this isn't going to be a big deal. You're going to remember these very quickly as soon as you see them. So an angle in standard position, here's what we're talking about. So we're going to think of this on our xy axis. So we've got our x and our y just like usual. So the vertex has to be at the origin, and then the initial side has to be on the positive x-axis. And then what we do is we rotate it. So you want to think of it like an angle of rotation. Generally, we rotate in the counterclockwise direction. So we would rotate like this. And then, so this would be our terminal side. So we have our initial side and our terminal side. This arrow is not part of the angle. I'm drawing it to indicate the motion that we're going in counterclockwise direction. So this would be a standard position angle in the first quadrant. In the second quadrant, let's draw a standard position angle in the second quadrant. So we might rotate it this way. And there's our terminal side in the second quadrant. So wherever the terminal side ends up, that's going to be, we'd call it an angle in that quadrant. So like if it's the second, terminal side's in the second quadrant, we would call it an angle in the second quadrant. I apologize, my dog is playing with a toy in the background, so you might hear some squeaking. Just try to ignore it. Let's do one in the third quadrant. So we can go this way, we can go all the way into the third quadrant. So this would be an angle in the third quadrant. So the measurement of this angle would be all the way around from the positive x-axis to wherever the terminal side stops. All right, describe how angles are generated. Okay, so if we rotate counterclockwise, which is what I did in the pictures above, this would be considered a positive angle. Okay? And so, like in this first picture, I'm estimating this might only be 60 degrees. Let's say maybe this would be like a 60-degree angle. In the second picture, again, I'm just kind of estimating because I just sketched this. Maybe this is 135 degrees, right? And then in the third picture, we might go past this line, which puts us into the third quadrant. Maybe it's 250 degrees. I'm not sure because I just drew this. But we're going to have angles that are larger than what you would think of in traditional high school geometry. So in high school geometry, you might have said an angle can't be bigger than 90 degrees. Well, I guess it could be bigger than 90 degrees. Angle couldn't be bigger than 180, really, in high school geometry. Now we're going to have angles that are bigger than that. So we can rotate counterclockwise, and that gives us a positive angle. On the other hand, if we rotate clockwise, that gives us a negative angle. So now we can have angles that are negative. Okay? An example of a negative angle in standard position, it might look like this. So same, we've got our XY axis, vertex at the origin, initial side on the positive x-axis. So maybe we rotate clockwise, and there's my terminal side. So this would be a negative angle because I rotated clockwise. It's a negative angle in the third quadrant because my terminal side ended in the third quadrant. So I'm not sure what the number is here. Maybe this is negative 120 degrees or something like that, okay? One way to measure angles is in degrees, which is symbolized by, remember the little degree symbol, little circle there. By definition, the ray has rotated, I guess they want 360 degrees to make a complete rotation. So that would be if I took my angle and I went from the positive x-axis all the way back to where I started with. That would be a 360-degree rotation. Let's see, a blank angle measures less than 90 degrees. You may remember that term from high school geometry. That would be called an acute angle. A blank angle measures 90 degrees. Remember, a 90-degree angle we'd call a right angle. And then angle measuring more than 90 degrees but less than 180 is called obtuse. All right. And then a straight angle, so one that's exactly like this, is going to be 180 degrees. Okay? So let's practice a couple. Draw each angle in standard position. So you want to think about what quadrant would this number put me in. That's really where you want to think about is where do I end up, what quadrant. So if I only rotate 45 degrees, notice it's positive, so I'm going to rotate counterclockwise. So we'll start out here on the positive x-axis, and then 45 degrees would only put me right about there, just a 45-degree angle, maybe right about there. I'm just drawing the arrow to indicate the direction of rotation. Try to get in the habit of drawing that arrow because the arrow indicates the direction, and that's important because if the arrow is not there, the reader doesn't know, are you rotating clockwise or are you rotating counterclockwise? It's hard to tell whether the angle is positive or negative, so try to include that arrow indicating the direction. 225-degree rotation. So think about what quadrant that would put you in. All right, before I draw it, think about what quadrant that would put me in. This would be 180, right? A straight angle would put me at 180. So if I'm at 225, I have to be past that 180. And that would put me into the third quadrant right here. So 225 would be right here. And then negative 135. So we're rotating now clockwise. Why? Because it's a negative angle. So we start off in the same location. So this would be, if I stopped here, that would be 90 degrees. I want to go 135. So distance-wise, I need to go a little bit further. And that puts me into the third quadrant. How do I know I stop in the third quadrant? Remember, this is 180 right here. This would be 180 to that negative x-axis. So I only want to go 135, so it puts me in the third quadrant. All right, so 405. Here's where it gets kind of interesting. If the angle is larger than 360, that means we're going to rotate more than once. So I'm going to start off on the positive x-axis again. So one entire rotation, remember, if I stop there, that's 360, but I want to go 405. So think about what quadrant that's going to land me in. If you say, what is 405, take away the 360 that I've already traveled, that leaves me another 45. So that means I need to go another 45 degrees, which puts me right back in the first quadrant. Notice that this starts and ends in the same location as this question over here did. these two angles. Notice they start and end. The terminal side, the initial and the terminal sides are exactly the same. What's different is the journey they took to get there. This one took a little bit longer to get there because it went all the way around plus another 45. There's a special name for that. That's an important relationship. And so that's called coterminal. So two angles with the same initial sides are called, let's read this again. Two angles with the same initial, oh, there's a typo here. This should say initial and terminal. Sorry about that. This should say initial and terminal sides are called coterminal. Okay? Two coterminal angles for an angle x can be found by adding 360 or subtracting 360 from x. Any angle has an infinite number of coterminal angles, but the way we can get multiple coterminal angles is by adding or subtracting 360 from whatever angle we're interested in starting at. Let's do a couple examples. Assume the following angles are in standard position. Find a positive angle less than 360 that is coterminal with the given angle. All right, so let's start with 420 degrees. So 420, first of all, let's figure out where that puts us. I always like to draw a picture. I think that kind of helps me keep everything straight. So let's draw a picture first. So we're starting here. All right, so if I'm going to go 420 degrees, that means I'm going to rotate 360. Now, how much further am I going to have to go to get to 420? So 420, take away 360. Gives me a difference of 60 degrees, right? So I'm going to go another 60 degrees right into the first quadrant. All right, so this is actually a really quick, easy way to find your coterminal angle. I can look at the picture and I can see. Let me see if I can get a different color here. I'm not sure how to change colors. All right, well, let me not worry about it, but I'll do a thicker one. So notice I started here and I ended at the same place, which makes them coterminal. So the two angles that are coterminal is the 420 that I started with and the 60 degrees. How did I get that mathematically? I did exactly what it said. Up here, I subtracted 360 from x. I could have added 360 and gotten a larger coterminal angle, but they specifically asked for one that was less than 360. So because I was starting out more than 360, I had to subtract 360 to get to another angle that was coterminal, okay? So this 60-degree angle would be coterminal with the original 420. Let's try this one, negative 120. Okay, so if we start here, and it's negative, so we're going to go backwards. Let's see, so I'm going to go backwards 120. So there's 90 right there, and I need to go another 30 degrees to get me to 120, which puts me right in the third quadrant, maybe a little further, so right about here. Okay, so that's the original angle is negative 120. Now, how can I get an angle that's coterminal? Well, first, I hope that you see one way to do that would be, based on my picture here, would be to say, okay, what if I went in the positive direction? This angle that I just drew would be coterminal because it starts and ends at the exact same place. Mathematically, how do I get that measurement? Well, we could do negative 120 plus 360, right? So let's see, 360, 260, 240. So what I literally did is I added 360 to the original angle, and I got 240, and that's the measure of this angle here, 240 degrees. I could have subtracted. I could have said 120 minus 360, 364. That would have been negative 480. If I were to draw negative 480, that would also be coterminal with the original angle, but they specifically asked for one that was positive. So I added 360 instead, and I got a positive angle of 240. That would be coterminal with the original angle, okay? All right, so one thing that is important that we're going to use a lot, and to be honest with you, when you get into calculus, everything is measured in what we call radian measure. We don't generally use degrees when we get to calculus. Engineers will use degrees. If you ever take an engineering class or something like that, they might use degrees a little bit more often. But when we talk about calculus, we generally work with radian measure. So radian measure is probably new for you if you haven't taken pre-calc before. Radian measure is another way of measuring angles. What is meant by radian measure? I won't get into all the details of where it comes from, but basically what you just need to remember is that it's another way of measuring angles. It says, what is the relationship between radian measure of an angle and arc length? So really what it comes down to is if we think about a circle, and again, I'm not going to get super detailed here, just need to remember that's another way of measuring angles. But you think about a circle, and that's really what you're talking about, right? So like when we draw these images, if we go 360 degrees, you can kind of think of it like a circle. It's the relationship between the radius of the circle, the circumference of the circle that's marked off by whatever the radius of the circle is. So if you think about, like if I have an angle like this, how much of the circumference is marked off by that angle, whatever that is, that would be considered radian measure. So it's another way of measuring angles besides using degrees. There's a formula that we might use, and by the way, this is called the arc length. So the arc length is the portion of the circumference that's cut off by that radian measure. We generally, when we measure radians, we sort of, as our base, we think about it as a circle with a radius of 1 unit. That's actually called the unit circle, which we'll talk about later in the chapter. The relationship, there's a little formula here. Arc length is always equal to the radius of the circle times the measurement of the angle, and we'll call that measurement theta. And theta would be, here, let's write that down. So theta would be the measure of the angle in radians. So when we talk about arc length, we use radian measure, not degrees. So this question, it says a central angle theta, so that's the angle right here, in a circle with a radius of 6 inches represents an arc of length 15 inches. So they're telling you the length of the arc that's cut off by that angle is 15 inches. The radius is 6. And it says, what is the radian measure of theta? So we're going to use that little formula I just gave you. I'm going to replace the arc length. So arc length is the S in the formula. I'm going to replace that with 15. The radius is 6. And then angle theta is what they're looking for. So if we divide by 6, of course, 15 over 6, I don't care about reducing. I'm just going to call it 15/6. So the radian measure that corresponds to that angle would be 15 over 6. Okay, so what is the relationship between degrees and radians? So when we talk about converting between degrees and radians, we always use a circle that has a radius of 1 unit, as I mentioned, that unit circle. And so for that reason, 360 degrees corresponds to 2 pi radians. Where does that come from? Let me just show you real quick. If I have a circle and the radius is 1 unit, remember the formula for the circumference of the entire circle. You don't have to write this, just watch for a second. The circumference of an entire circle is 2 pi r. You might remember that from geometry. If you don't remember that formula, not a big deal. So the circumference of this entire circle would be 2 pi times the radius, which is 1 unit, because we just said it's a unit circle. The radius is 1, right? 1 unit for the radius. So the circumference of the entire circle is 2 pi. So what they're saying is if I travel 360 degrees, well, think about the measurement. That's 1 trip around the entire circle. So what we would have said 360 degrees for the angle in degrees, in radians, we're going to say it's 2 pi. How about 180 degrees? So 180 degrees would be half that same distance. So in degrees, that would have been from here to here, right? That straight angle. So half of the entire circumference of 2 pi, if that's the entire circumference, half of that would just give me pi. So 180 degrees always corresponds to pi radians. That's the conversion factor we're going to use to go between degrees and radians. So to convert from degrees to radians, we're going to multiply degrees by pi over 180. So to go from degrees to radians, we multiply by pi over 180. To go backwards from radians back to degrees, we multiply by 180 over pi. So it's just a ratio that we use to convert between the two of them. Let's do some examples. This is not as complicated as it sounds. Let's do some examples here. Convert each angle from degrees to radians. So we're starting off with 30 degrees, and they want me to convert that to radians. So I'm going to multiply by 100 or pi over 180. That's my conversion factor. And leave your answer in terms of pi. one way to remember this is you kind of think of the degrees are dividing out. You may remember back to science class where you convert between units and you look for the units to divide out. It's the same idea. Always reduce these to lowest terms. That will help you later if you get in the habit of doing that for these questions. Of course, they both divide by 10, and then 3 goes into 18 6 times. So this is a 1. So that gives me pi over 6 radians. That's the equivalent. Let's try the next one, 90 degrees. So we're going to multiply that by pi over 180 degrees. Of course, the degrees cancel. The zeros are going to cancel out. 9 goes into 18 twice. So that leaves me with a value of pi over 2. Right? 1 times just the pi over 2 after I reduce. And then the last one, negative 135 degrees times pi over 180. I'm going to grab my calculator here to help me with the numbers. Of course, the degrees we see are going to cancel. I know both of those are multiples of 5, but I believe they're also multiples of 15 as well. So let me double check. So 15 goes into 135 9 times. And then 15 goes into 180. Oops, wait a minute. 12 times. So actually, those reduce again, don't they? 9 and 12 will both reduce again. So I think 45 was the multiple I should have used, the largest common multiple. I use 15, not a big deal, just reduce them again. 9 divided by 3, of course, is 3. 12 divided by 3 is 4. So what do I have? I have negative, of course, don't forget the negative. Negative 3 pi over 4. And I didn't do this, but if you want to put these over 1, if that helps, you can do that, of course. So negative 3 pi over 4 is what that reduces to. All right, so then let's go back in the other direction, convert from radians back to degrees. So we'll start with pi over 3. To do that, remember what we're going to do. We're going to multiply by 180 over pi. When you convert back to degrees, the pi should divide out. So these pi's divide out. 3 goes into 180 60 times. So we're left with 1 times 60, which is just 60 degrees. Letter B, we've got negative 5 pi over 3. Multiply that by 180 over pi. Of course, the pi's go away again. 3 goes into 180 again 60 times. 60 times the 5 that's there gives me negative, don't forget, 300 degrees. Finally, letter C. This one's a little different. It's like 1. A lot of times we measure with radians, they're going to have that pi value in there. But sometimes if it's an unusual angle, it may not have that. This is just 1 radian. So 1 times 180 over pi. Normally I say leave the pi in your answer, but this would leave me with a value of literally 180 over pi. And that's a little hard to explain what that means. It's hard to kind of picture where that would be on the circle. So I would go ahead and change this to a decimal. Literally in your calculator, do 180 divided by pi. And let's see what that is as a decimal. I'm getting about 57.3. So this would be 57.3 degrees. So this would be an angle in the first quadrant. You see what I mean, though, that the pi really by itself doesn't mean much in this question. You know, 300 degrees, I can draw that. 60 degrees, I can draw that. Where's 180 over pi? I can't really draw that. So this would be one where I think it makes more sense to change it to a decimal because I can figure out where 57.3 degrees approximately is on the circle when I draw the angle. All right, let's do a couple other examples here. So it says, find one positive and one negative coterminal angle for each of the following in radian measure. All right, so here's where we need to be a little bit careful. So to find coterminal angles earlier, remember what we said for coterminal, we said that we were going to add 360 or subtract 360. So we do that if we're working with degrees. However, if we're working with radians and we're asked to find coterminal angles, we can't use those numbers anymore because now we're working with radians. So remember, 360 is equivalent to 2 pi radians. So we're going to use 2 pi instead. So make a note here that because we're dealing with radians, we're going to add or subtract, depending on what we need, 2 pi this time to get coterminal angles. So let's try the 13 pi over 6. Let's do an example. So here's where you're going to be really comfortable with adding and subtracting fractions because we're going to use them quite a bit in this section. So 13 pi over 6, let's add 2 pi. So this is really 2 pi over 1. Remember when you add fractions, you have to have a common denominator. So the common denominator would be 6. So I'm going to multiply this by 6. That gives me 13 pi over 6 plus 12 pi over 6. And that gives me 25 pi over 6. So one angle that is coterminal with the original angle would be 25 pi over 6. They asked for one negative angle. So to get that, we're going to need to subtract 2 pi from the original angle. And remember, that was 12 pi over 6. So let's write that. So 13 pi over 6 minus 12 pi over 6. So 13 pi minus 12 pi gives me 1 pi over 6. Now here's the kicker. That is coterminal with the original angle. So now what I've done is I've found two positive coterminal angles with the original angle. However, they wanted one that was negative as well. So to do that, I'm going to repeat the process. So take your pi over 6 that you're at and subtract the 2 pi again. Remember what 2 pi was? 2 pi was 12 pi over 6. So subtract 12 pi over 6 again, and that gives me a value of negative 11 pi over 6. There are an infinite number of coterminal angles. I have actually found 3 of them in this process. So one that was positive was 25 pi over 6. Another that was positive was pi over 6, and then they wanted one that was negative, which was negative 11 pi over 6. So you can keep adding and subtracting 2 pi or 360 if you're in degrees as many times as you need to get the coterminal angles that they're asking for. Let's do another one, 3 pi over 4. So I'm going to start by adding 2 pi over 1, which of course the common denominator is 4. So I'm going to multiply by 4 on the top and bottom. I have 3 pi over 4 plus 8 pi over 4, which gives me 11 pi over 4. So one angle that's coterminal with the original is 11 pi over 4. Let's subtract, here let me make a little bit of space here. Let's subtract 2 pi to get another angle, and let's see what happens. Let's get rid of all this for a minute. Okay, so let's go back to the original angle, 3 pi over 4 minus 2 pi over 1, which of course was 8 pi over 4 once I got the common denominator. And so 3 pi minus 8 pi gives me negative 5 pi over 4. So that would be a negative angle that is coterminal with the original angle. So there's two right there, one positive, one negative. Let's do one more, negative 2 pi over 3. So I'm going to add 2 pi over 1. Common denominator this time is 3. So I have negative 2 pi over 3 plus 6 pi over 3 gives me negative 2, positive 6 gives me 4 pi over 3. So a positive angle that is coterminal with this original angle is 4 pi over 3. Now we need a negative angle as well. So I'm going to take negative 2 pi over 3 and I'm going to subtract, just so I don't have to do all this again because I'm short on space, I'm going to use 6 pi over 3 right away. Notice that's your 2 pi. That's your 2 pi. I'm just using 6 pi over 3. That's the common denominator. So negative 2 minus negative 6 gives me negative 8 pi over 3. So there is your other angle that's coterminal. We could do this all day long, or keep adding and subtracting 2 pi all day long, and I'd just get multiple angles that are coterminal with the original. Okay, a circle has a radius of 4. It says find the length of the arc intercepted by a central angle of 240. So remember our formula, S equals r theta. S is the arc length, r is the radius, theta is the angle. But here's the trick, theta must be in radians. Remember that, theta must be in radians when you're talking about arc length. So for that reason, I have to convert this 240 to radians. So let's do that. Let's convert 240. To do that, remember we multiply by pi over 180. Let's see, so the 10s are going to cancel. These are both divisible by 6. 6 goes into 24 4 times. 6 goes into 18 3 times, so I'm left with 4 pi over 3. So 4 pi over 3 is the equivalent angle of 240 using radian measure. If I draw them out, they're going to be exact same location on the circle. One's just radians, one's degrees. So let's come back over here to our formula. It says find the arc, the length of the arc intercepted with a radius of 4. So r is 4. And then theta is the 4 pi over 3 that I just computed. So if you want to put that over 1, you can. Nothing reduces here. That gives me 16 pi over 3. And we'll use the units. It was inches for the radius, so the arc length would also be in inches. Okay, we could make that a decimal, but I'm going to leave it for now. All right, last little thing here. Two positive angles are complements if they sum to 90 degrees. Angles that are complementary add up to 90 degrees. Two positive angles are supplements if they sum to 180 degrees. Supplementary angles add up to 180. So find the complement and the supplement of the given angle. So for the first one, for the complement, I'm just going to do 90, subtract the 73. Let me see. So that gives me an angle of 17 degrees, right? 17 degrees. So my complementary angle is 17 degrees. For the supplement, I'm going to do 180 minus the 73. So let's check out what that gives me. So 180 minus 73. Let's see. I'm using my calculator. I'm cheating here. That gives me 107 degrees. So that would be the supplement to the original angle. The 17 would be the complement. Let's try this one. Now, this one, there's not really a complement. We're only working with positive angles. We talk about these. So there is no complement because it's already over 90. So we'll just do the supplement. It's going to be 180 minus the 110. So my supplementary angle would be 70. So 70 and 110 would be supplementary angles. And so that's it for this section. I just kind of wanted to get you used to some of these definitions and really focus on converting between radians and degrees because that's going to be a really, really important skill we're going to use quite a bit in this section.